forgot to start the recording. Here we are, lecture 20, the second half of section 5.3. And we're going to start with this theorem about continuous functions on closed and bounded intervals. And the conclusion is the image of a closed and bounded interval is also bounded. Both of the hypotheses, closed and bounded, are necessary. Let's just look at that real quick. If I isn't closed, well, we could look at f of x equals 1 over x on the open interval 0 to 1, then, right, f of I would be, what would the image of that open interval be?
Would it be 1 to, well, I guess you could say infinity, so to speak?
Mm-hmm. Yep, 1 to infinity. Yep, so here we take a bounded interval, but it's not closed, and the image is not bounded. Okay? What about if I isn't bounded? What's going to be our closed interval? I don't know, 1 to, 1 to x. No. 1 to infinity is a closed interval, right? And I don't know, let's take our function to be x. Then again, we get an unbounded range. Okay? So we certainly need both of these hypotheses. We can't remove either of them. Good. Any questions before we just jump into the proof? Okay. So a closed and bounded interval and a continuous function. Now, the proof is a pretty straightforward application of Bolzano-Weierstrass. Okay, Bolzano-Weierstrass is going to give us the. I'll get to your question in a second, Alexis. Bolzano-Weierstrass is going to use the closed and bounded thing. That's the hypothesis in Bolzano-Weierstrass. And then continuity is going to connect us between, we're going to use the sequential version of continuity. Okay? That's how the proof is going to fit together. Alexis asked if the quiz was going to cover 5.1. I guess the quiz will kind of cover 5.1 because it's going to be all about continuity. But I'm not going to particularly put questions for 5.1 on there. There wasn't much in 5.1 if I remember correctly. Okay, so let's do the proof here. I didn't spend any time thinking about this. I don't know if there's a way to do this without a contradiction. It's nice, but we're going to do it with a contradiction. So let's suppose to the contrary that we have our hypotheses. So I is closed and bounded, and F is continuous, but F of I is not bounded. Okay. Now remember this not being bounded, this goes back to chapter 2, right? A set is bounded if we can find any upper bound and lower bound. So what this means, if you're not bounded, well, I'll write it here. Therefore, for every natural number, little n, there has to be some point in our interval such that the absolute value of f of xn is greater than n. Okay. And that's true because if that weren't true, then little n would be a bound on f of I. Okay, so what's our picture here? What we're doing is we've got, we found an x1 where f of x1 is greater than 1, and we found an x2. Then we found an x3. Then we found, let's say, an x4. Yeah. We're finding bigger and bigger values of f. Inside this interval, this closed and bounded interval I. Okay. Let's go on and apply the Bolzano-Weierstrass theorem. Since I is bounded, so is the sequence xn. The values of the sequence come from a bounded set, and that's what it means for a sequence to be bounded. So the point is that Bolzano-Weierstrass shows that it has a convergent subsequence. Let's give that convergent subsequence a name, xnk. Any questions so far?
I have a quick question.
Go ahead.
For the xn's, those aren't necessarily unique, correct? There could be more than one xn such that f of xn is greater than n. So how exactly do we pick the xn's for our sequence? Do we say something like let the xn be the smallest such x that f of xn is greater than n?
No, you don't need to worry about it. Okay, so we never claimed there that the xn's are different or anything. We never made any claims about the xn's except that they do that one thing. So my picture is misleading.
Okay, thank you.
So if you think about it, whatever you have for x3 would be a fine x2 or a fine x1. Okay. But actually, they do have to change eventually. Right? Because we've got an infinite sequence of these things. So maybe you've got one that's like f of x 1 million is 1 million. Well, then that can be the first 1 million terms of the sequence, but then x of 1 million and 1 has to be something else. Right? Eventually, you will exceed whatever function value you have. Eventually, little n will exceed whatever function value you have at that value of x.
That makes sense. Okay.
Okay. So yeah, we're just not assuming anything special about these except that they do that one thing. Okay, and Bolzano-Weierstrass doesn't care. Bolzano-Weierstrass doesn't care if your sequence repeats values. In fact, from the point of view of Bolzano-Weierstrass, which is just guaranteeing you a convergent subsequence, if your sequence repeats values, it's even happier. Right? I mean, in some sense. Okay? If a theorem can have feelings. Okay. It's a convergent subsequence, so we should give its limit a name. Right? Let's define x to be, let's make it x star to be this limit of x and k. Now, I claim that x star is in I. And I'll explain this kind of parenthetically here. Let's say that I is the closed interval from A to B. Okay, so if I is the closed interval from A to B, then each of the x and k's is in I, so each of the x and k's lies between A and B. Okay. So why does the limit of the x and k's lie between A and B? So it's not the intermediate value theorem, because the intermediate value theorem is a thing about functions. So what I want to do here is write this. And fill in that blank. Yeah, squeeze theorem works. Okay? Squeeze theorem says if all the terms of a sequence are between, the terms of two different sequences, then the limit is between the two limits. Here our other sequences are just these constant sequences A and B. Okay. Oh. Yeah, that's a good point, Madeline. She suggested the squeeze theorem and then pointed out that it's not quite right. I'm going to just call it a fact about limits. Because I can't remember exactly how we stated the squeeze theorem. Where is my textbook? How was the squeeze theorem stated?
There's theorem 3.2.6.
Yeah.
Is this? to use this theorem to prove the squeeze theorem.
Yeah, okay. So I was trying to avoid. I know it's 326 because I've happened to remember that number. I was trying to avoid using that number because obviously you don't use those numbers when you talk about it. So there is a fact about limits that tells us that this is true. Right? Notice though when we do this, it's because we've got a less than or equal to here. If we just had, if we had a strict inequality, when we took the limit, we would not get a strict inequality. You think about like 1 over n is greater than 0 for all n, but its limit is not greater than 0. Its limit is 0. Okay, so I'm perfectly happy calling this a fact about limits. Any questions about that before we go on?
So how exactly is it that we know that fact?
Well, if you insist, it's theorem 3.2.5.
And 0.6 also.
Oh, sorry, 0.6. Yeah.
But for 0.6, it uses the proof from 0.5 just 2 times, basically.
Yeah, I mean, so what that theorem really says, the easiest thing about the theorem is that if xn is greater than or equal to 0 for all n, then the limit of xn is greater than or equal to 0. And that's the easiest way to prove it. And I think actually, didn't we have an exercise where we proved this? Maybe I'm misremembering. But for our purposes right now, I'm happy to just say that this is a fact that we remember from limits, if that's okay. Okay. All the terms are bounded below by a, so the limit's bounded below by a. They're all bounded above by b, so the limit's bounded above by b. Okay, and since that's what it means to be in a closed and bounded interval, right? I forgot I wanted to mention that. Because I is given as a closed and bounded interval, we know we can write it as the closed interval from a to b for some real numbers a and b. Okay, so the whole point of this was to get this conclusion that x star is in I. And now what is our problem? So remember, we assumed to the contrary that f of I is not bounded. So we need to get a contradiction. What is our contradiction?
We need to find some n that's greater than all values of fx, or the absolute value of fx. Or find something small, something like that.
Sort of. So we haven't used continuity yet, have we?
No.
So let's use continuity. Remember, we've got the sequential form of continuity. Because f is continuous on I, Okay. If we look at the limit of f of x and k, because the x and k's converge to x star, their function values are supposed to converge to f of x star. Why is that a problem? Anybody? So the xn's are all places where f has a large value, right? Well, so that f of xn is greater than n. The absolute value of f of xn is greater than n. Well, the nk's are just the sum of the n's. So f is really big at the nk's too. Okay. So what does it mean? Well, f of nk is greater than nk for all k. That means the limit of these function values does not exist. Okay, remember, we don't allow limits to be infinite. And in fact, we couldn't conclude this one was infinite anyway, because it could be oscillating positive, negative. Okay? So we said, because it's continuous on this interval, this limit has to exist and has to equal the function at the limit of the sequence. But now we just said the limit cannot exist. Okay, that's a contradiction. So this contradicts the above fact that because f is continuous, the limit of nk, f of x of nk, equals f of x star. And this contradiction proves the theorem. Okay. Okay, any last questions about that result? Well, one more.
So we use the bounded part as our contradiction starter, I guess, and the closed is to guarantee x star is an I.
Yes.
Okay.
Yes. If we repeated this proof, let's go back to one of our counterexamples just for a minute. Let's look at the first counterexample, or the first, not counterexample, but example. If we were trying this, if we were following this proof with the function 1 over x on the interval 0 to 1, well, the xn's we're looking at would be getting closer and closer and closer to 0. Okay? But then when we went and we took the limit, and actually, so Bolzano-Weierstrass stress wouldn't even be needed there. Just the xn's themselves converge. But when we look at what they converge to 0. Okay? And in this case, 0 is outside of the interval. Okay. So if we didn't assume that was showing that if we didn't assume the interval was closed, then we couldn't finish this proof. Okay. And Daniel's right about Madeline's question. That is our next theorem and our last theorem for today. What about closedness? So continuous functions preserve intervalness. If the interval is closed and bounded, they preserve boundedness. And now if it's closed and bounded as well, they preserve closedness. Well, yeah, but we're going to state it a little bit differently, closer to what you saw in calculus. Okay. First, we need a definition. Let's have a domain and a function. And we will say that f has an absolute maximum on A. That's the term we're defining. If there is some point I'll call it x plus, where it's bigger than anywhere else. Well, not strictly bigger, weakly bigger. Okay. Just to save 30 seconds, I'll note that there's an analogous definition of absolute minimum that I don't think I need to write down. Okay. Now, I believe this is a theorem you learn in Calculus 1. I could be wrong. I'm going to call it the extreme value theorem. So we have the IVT and now we have the EVT. I'm going to add one more hypothesis. Yeah. I'm going to add one more hypothesis. I need the interval now to be non-empty. And again, we're going to take a continuous function defined on I. And then our conclusion is that then f has an absolute maximum and an absolute minimum on I. No. I'm certainly not saying that f can't have more than one absolute maximum or absolute minimum. Note that if you had two absolute maximums, say, absolute maxima, then your function values would be the same at both. Okay. So, like, if you look at the constant function, every point is an absolute maxima and every point is an absolute minima. Okay, so that could certainly happen. You can have more than one. So there's no uniqueness here. The other thing I'd like to point out is that our proof is not going to use the intermediate value theorem. Okay, so this is, I've written this so it's completely separate from the intermediate value theorem. If you combine the extreme value theorem with the intermediate value theorem, what you get is that under the same hypotheses, so under these same hypotheses, you can conclude that the range f of I will itself be a non-empty closed and bounded interval. Okay, you get non-empty just because I is non-empty. You get interval by the intermediate value theorem. It says you map an interval to an interval. Then you get bounded. Oh, I'm sorry. I mean, also use the previous theorem too. You get bounded by the previous theorem. And then you get closed because the extreme value theorem tells you you have bound. You have an absolute, sorry, not bounds, but you have an absolute maximum and minimum. So that's telling you that it really is a closed interval. Okay. So that would be if you combine those two results. Questions about the statement of the extreme value theorem before we start the proof? No? Okay. We're just going to find an absolute maximum. To find an absolute minimum, it's the same thing, and you can just plug minus f in there. A minimum of minus f is a maximum of f. Well, the location is the same. The values are negatives. Okay. So what do our hypotheses say? Our hypotheses say that, okay, so first of all, we're going to use our previous theorem. Our function values are bounded. And whenever we see bounded, we should think, oh, supremum and femum. Okay? Except there's one more hypothesis we need, and that's the non-empty thing. Okay? So our hypotheses say that I is non-empty. So the range is non-empty. Okay. That's just because by definition a function has to map something in its domain to something. Okay? So its range can't be empty. By the previous result, f of I is bounded, yes.
I don't mean to be picky, but you didn't do a not equal on the fi. You're saying that it is the empty set.
Thank you. Yes, that's a typo. The range is not empty. Okay, so it's not empty and it's bounded. Therefore, it has a supremum. Again, like I said at the beginning, we'll say something about an absolute min at the end. Until then, we're just going to work on absolute max. Okay. Well, let's give that value a name. Let's let u be f of I. Now, that's the supremum, so that's a least upper bound, or the least upper bound on the values of f. So all we need to do to show that we have an absolute maximum is to find a point that maps to u. Okay? If we find some x plus such that f of x plus equals u, I'll write that over here. If we find an x plus that does that, then we're done. It's greater than or equal to every other value in the range, because right? Being an absolute max is better than being a supremum, because being a supremum just means you're at least upper bound. It doesn't mean you're actually achieved. Okay. Now, we do our standard trick. We subtract a 1 over n from the supremum, and that's not the supremum. So there's something in the set that's bigger than it. Okay. So I'm, just for time, I'm going to write this a little bit more briefly than I normally would. For every natural number n, there is some point in the interval such that, right, if I subtract 1 over n from u, that's not the supremum. So there is some point xn that's greater than n. Sorry, whose function value is greater than n. But on the other hand, it's got to be at most u. Okay. Now we played the same exact Bolzano-Weierstrass game. By Bolzano-Weierstrass. Okay, the xn's are still contained in I. I is bounded. So they have a subsequence that converges. Okay. Let's give a name to the limit. We'll call it x plus. And now you think again back to the other proof. In the other proof, we said that since all the x and k's are in this closed bounded interval I, the limit is also in the closed bounded interval I. So for the same reason, so as in the previous proof, x plus is in I. Good. Now, this time we can actually use the squeeze theorem, literally the squeeze theorem. What does the squeeze theorem say? Well, first of all, how do we apply it? We're looking at the f of x and k's. They're between u minus 1 over nk and u. The sequences, the sequence u minus 1 over nk and the sequence, the constant sequence u, both converge to u. Okay, since that is true for all natural numbers k, we have that the limit of the fnks is equal to u.
Should that be x sub nk?
Thank you very much. Yes. Okay. And last thing, we never use continuity. The sequential form of continuity says that we take a bunch of function values, then they have to converge to the function at the value that they're converging to. So because f is continuous, at x plus, we have that, well, f of x plus is equal to u. Let me write out another step. It's equal to this limit. Which is equal to u, which is the supremum of the range. Okay. Therefore, there can be no bigger function value on I. So x plus is our absolute maximum. Okay. Finally, to get an absolute minimum, I mean, you could just repeat this exact argument, replace supremum with infimum, replace all your inequalities, it works out the same, or apply this, apply the above to the negative of your function. Okay. So that's the end of that proof. And let me just, as I said before, if you combine the extreme value theorem and the intermediate value theorem, you see that f of a non-empty closed interval is another non-empty closed interval, as long as f is continuous, of course. Okay. And then you think, do I need non-empty? If we take a continuous function and we applied it to the empty set, we would get the empty set. The empty set is a closed interval, so the range would also be a closed interval. So actually, in that case, we can remove that word non-empty. A continuous function on a closed interval is a closed interval. Sorry, the range of a continuous function on a closed interval is a closed interval.
I'm good.
Okay, so I almost finished on time there. I will stop the recording. Now I have to start recording again because you're right, I said something stupid. I totally forgot about closed and bounded interval. Yes. So we have to fix this. This is a closed and bounded interval is a closed and bounded interval. Thank you. Okay. We don't need non-empty because the empty set works.